Thank you everyone for joining our latest in our global webinar series. I'll be your host for today's webinar. My name is Wilmer Compagnoni, and today we will be covering MLCC and film capacitor basics. We have two of our members of our different business groups, Mark Lapps from the ceramic business group and Daniele Zanarini from our film business group, and they'll be taking us through the basics of film, MLCC, and film capacitors. Before we get started, I would like to remind everybody that if you do have a question, we will address them toward the end of the webinar, but please submit them through the Q&A portion of the Zoom window. And when Mark and Daniele are done with their presentations, we will address those questions at that time. So with that, the first one up on the roster is Mark Lapps, and he'll be taking us through some of the basics, construction characteristics of MLCCs. So Mark, if you please.
Let me share my screen. Wilmer, let me know when you can see it.
Yes, we can see it.
Excellent. Hello, everybody. My name's Mark Lapps, Technical Product Manager for the Ceramics Business Group here at KEMET. I have a bachelor's degree in electrical engineering from the University of South Florida, and I've been employed at KEMET since 2006 as an electrical test engineer, and then a technical product manager ever since 2016. So for today, we're going to cover MLCC construction, various dielectrics, then go into MLCC characteristics and key design considerations, and then some key takeaways of the presentation. So ceramic capacitors come in a variety of dielectrics, form factors, and sizes. These are driven by key application characteristics such as capacitance, voltage, temperature, and mechanical and reliability requirements. For example, applications with extreme vibration requirements may need ceramic capacitors with some type of mechanical absorption, such as lead frames. And here at KEMET, we offer many different form factors, such as surface mount, axial and radial leaded, lead frames, arrays, and many others. But for this presentation, we're really focused on multi-layer ceramic capacitors, or MLCCs. Now, MLCCs are in just about every electronic device that's made today. In 2018 alone, suppliers shipped almost 4 trillion MLCCs, covering applications ranging from consumer devices, vehicles, to satellites. Now, as electronics proliferate in our everyday life, the demand for MLCCs is going to continue to grow. For example, today, almost every EV shipped has over 10,000 MLCCs, and each smartphone now has over 1,000 MLCCs. So, as these electronics grow, more MLCCs, more demand. Now, MLCCs are constructed using alternating layers of ceramic dielectric and metal electrodes. Each layer represents a single capacitor, and adding additional layers adds more capacitance to the MLCC since they are in parallel. Now, this is where we get the term multi-layer ceramic capacitor. We calculate capacitance using the capacitance equation that we see right here. The parameters for calculated capacitance are the dielectric constant, or permittivity, overlap or active area of the electrodes, the ceramic thickness, which is the dielectric thickness between these electrodes, and the number of electrodes. Now, for any capacitor supplier, capacitance is king. It's the most important thing. So the more capacitance you can cram into the smallest possible package, the better. So suppliers spend many R&D dollars to get as much capacitance as possible into this small space. Now, by looking at the parameters, if we increase the dielectric constant, the area of the electrodes, the number of layers, we're going to get an increase in capacitance. We can also choose to reduce the dielectric thickness, since capacitance is inversely proportional to that dielectric thickness. Now, if you're able to reduce the ceramic thickness in half, for example, you would essentially double your capacitance based on this equation. Now, because you've reduced those individual layers, you can actually fit more of those layers into the capacitor. So if you decrease those layer thicknesses by half, you can double the amount of layers, and the net effect is you get a 4-fold increase in capacitance just by decreasing the thickness in half. So one of the main goals for MLCC suppliers is to get as thin of layers as possible. Now this shows an exploded view of an MLCC. You can see the ceramic dielectric material along with the internal electrodes. MLCCs are made using either PME precious metal electrodes or BME base metal electrodes. Now historically, MLCCs were made from PME materials in which their electrodes were made from precious metals such as silver, palladium. Now over time, as dielectrics became thinner and cost needed to be reduced, suppliers switched over to BME materials in which the electrodes are made with either nickel or copper. Now today, the overwhelming majority of MLCCs use base metal electrodes such as nickel. Now to connect the internal electrodes to the outside world, the termination layer is added, which is usually made from copper. Then a layer of nickel, which acts as a barrier layer before the plating finish is added. The nickel layer is essentially to prevent dissolution of the during the soldering process. Now, MLCCs are manufactured using a variety of dielectric materials. We categorize these dielectrics into 3 classes, which refer to the capacitance stability over temperature. This slide shows some of the dielectrics that KEMET offers. The 3 classes are class 1, which is considered temperature compensating, and their capacitance shift is very low over the entire operating range. Class 2 and 3, which are less stable, which means that their capacitance will have some shift over the operating temperature range. However, Class 2 capacitors will have a much higher dielectric constant, which means you can get more capacitance in the same K size and voltage as compared to Class 1. Within each of these classes, we designate the dielectric using 3 characters such as C0G, U2J, which is defined by the EAA 198 specification. For some military and high reliability dielectrics, they use 2 characters, and they're similar to the X7 or the X7R C0G dielectrics, but there's a voltage component to the capacitance. Now we're going to go into the design and characteristics. Now again, MLCCs are categorized by those 3 classes, again, which refers to its capacitance stability over temperature. Here we can see the trade-off between the dielectric constant K versus the operating temperature. Now, since capacitance is proportional to the dielectric constant, any change in the dielectric constant will result in a change in capacitance. For class 1 dielectrics, such as C0G and U2J, the dielectric constant is relatively low, usually below 100, which results in a lower capacitance value compared to class 2 and 3. However, class 1 dielectrics are very stable over temperature, which makes them ideal for applications such as resonant converters, filters, and wireless power transfer. Class 2 dielectrics, for example, X5R and X7R, have a relatively high dielectric constant, somewhere between 1,000 to 4,000, so you'll see a much higher capacitance value for these dielectrics. For example, an 0603 10-volt C0G can have a typical capacitance around 15 nanofarads, whereas in the same K size and voltage for an X7R can have greater than 2.2 microfarads, so over an order of magnitude. Or 2 orders of magnitude. Now, although class 2 MLCCs have a higher dielectric constant, higher capacitance, their stability over temperature is lower. Now, you might see a capacitance shift of up to 15% at 125 C for an X7R, for example. These dielectrics are ideal for applications such as decoupling, bypass, and bulk storage. And then you have class 3, such as Y5V, Z5U, much higher dielectric constants above 10,000, but their stability is very poor. Now, because of this, they're not as widely used as class 2 dielectrics. So again, the majority of capacitor dielectrics are divided into subclasses, which are designated by 3 characters, which define its temperature coefficient of capacitance, or TCC. Class 1 dielectrics have a temperature range of -55 C to 125 C, and the 3 characters define how much that capacitance can shift over that temperature range. Now, since class 1 capacitors are considered very stable, their capacitance change is given in ppm per degree C and not percent. The first character defines the significant figure of the temperature coefficient. Second character defines the multiplier of that significant figure. And the third character defines the tolerance of the temperature coefficient. So for example, C0G, that's 0 times -1, which is 0, plus or minus 30 ppm per degree C. So the TCC for a C0G, for example, is 0 ppm plus or minus 30 ppm per degree C, and that's about 0.3% capacitance shift at 125 C. U2J, for example, is 7.5 times -100, so that's -750, plus or minus 120 ppm per degree C, which is about 7.5% at 125 C. U2J, even though U2J does have some temperature or shift in capacitance versus temperature, it's very linear and predictable. So class 2 and class 3 dielectrics are specified differently. Now, because these dielectrics are not as stable as class 1, their capacitance shift is given in percent and not ppm. The first character defines the minimum operating temperature range. The second character defines the maximum operating temperature range. And the third character defines the maximum capacitance change over the entire operating temperature range. So class 2 X7R minus 55 C to 125 C, and it can shift up to 15%. Class 3, for example, Z5U, operating temperature range of 10 C to 85 C, which can shift to positive 22% or minus 56%. So you can use the characters to figure out what the allowable capacitance shift is over the operating temperature range. So another design consideration is the capacitance shift on class 2 and 3 dielectrics when DC voltage is applied. This is called voltage coefficient of capacitance, or VCC. Now this slide shows the capacitance change for an X7R 1206, 10 microfarad, 16 volt, from 0 volts to 16 volts. Now, as you can see, as DC voltage increases, the actual capacitance will decrease. Now, the amount that the capacitance will drop will depend on the dielectric material, design, and applied voltage. Higher voltages mean higher dielectric fields on the MLCC layers, which increases this effect. Now, there's no specification for VCC for standard MLCCs. There are for some military part types, but not standard. So if you need to find out what the voltage coefficient of the capacitance is, you can go to our KSIM tool. So with larger case sizes, usually VCC performance is much better as compared to a smaller case size. So one of the key contributors to this effect is the voltage on the actual layers in the MLCCs. As you start downsizing an MLCC, for example, 1210 to 0805, we need much thinner layers, and this effect is multiplied. So you can see at 6 volts, you're only talking about a couple % drop for the 1210, as opposed to the 0805, which loses about half of its capacitance. So if you're considering going from a large case size to a small case size and you're downsizing, you have to consider the VCC effect and what it's going to do to the performance of the MLCC. There we go. Now the capacitance stability with voltage is not just DC, but also AC. As you can see here in the actual capacitance measurement of an X7R 1206 10 mic. This shifts from minus 8% at 100 millivolts to a positive 8% at 2.5 volts. Now, when we list a capacitor's rated capacitance in a data sheet, for this example, 10 microfarad, we measured it at 1 kilohertz, 1 volt RMS as the reference voltage. All capacitor measurements should be performed at the frequencies and voltages that are listed in the data sheet. Now, why is this important? Now, one of the top questions that we get on class 2 capacitors when it comes to the capacitance measurement is due to this reason. Here we can see an actual capacitance measurement of a class 2, 1210, 10 microfarad, 10% tolerance MLCC using one of the top of the line meters, or LCR meters. And this cap's actually measuring out of spec. Now the instrument has been calibrated and compensated. The AC voltage that we've applied is 1 volt, and we've measured it at 1 kilohertz. Now this is per the data sheet, yet we're measuring 8.3 microfarads, which is out of spec. Now why is that? Well, down here, the meter actually outputs the actual voltage that's being applied to the MLCC. Now, all capacitance meters have some source impedance, which is called ZS, and it's usually between 1 ohm to 100 ohms, depending on the model. Now, capacitors also have an impedance, which we'll call here Z cap, and as capacitance increases, its impedance will actually decrease. Now, if it starts to get low enough, you get a voltage divider across the instrument's output impedance, and you get a voltage drop across the capacitor. Now, as you increase capacitance, you can see here, this is based off a 100 ohm output impedance, which is pretty standard for some meters. As you start to get above 1 microfarad, you start to see a voltage drop across the capacitor, and you get to about 10 microfarads, and now you've lost the majority of your voltage across that capacitor, and based on that previous plot, you're going to lose some of your measurement accuracy. Now, the reason you see this jump here is because when you switch from 10 microfarads and above, you switch from 1 kilohertz to 120 hertz, which increases the impedance and it goes up a little bit. But again, you're still in this danger zone. Now this starts to become an issue again above about 1 microfarad. So how do you avoid this? Well, if measuring class 2 capacitors above 1 microfarad, it's important to select a meter that can, this is the first example, compensate for the voltage drop using what's called the ALC function or auto leveling control function. And that compensates for that source voltage. So now when you specify 1 volt and you turn on the ALC function, that's by the star here you can see, it'll actually measure the output voltage and then compensate, increase its output power so that it can get 1 volt across the capacitor, and now you're measuring within specification. Now some LCR meters have the available, can be available with low output impedance, which means that even for high capacitance MLCCs, there's very little voltage drop. And this is actually the preferred method because these meters are much faster because it doesn't have to compensate and correct. And it, you actually have that additional functionality, so they're actually much cheaper. So when measuring an MLCC, these are good meters to select with a very low output impedance because you don't have to worry about that ALC function. So again, ALC function or a capacitance meter with a low output impedance. So it's important to note that class 1 MLCCs are ultra stable over both DC and AC voltages, so no change in capacitance. And this is what makes them ideal for applications such as resonant power converters and wireless power transfer circuits. So capacitance can also change over time, which is called aging, and it's another factor that needs to be considered with class 2 or 3 MLCCs. Now, class 2 BME dielectrics are made from a barium titanate material with a Curie point around 130 degrees Celsius. The Curie point is the temperature at which the crystal structure of the dielectric material changes from a tetragonal shape to a cubic shape. Now, MLCCs will usually see this temperature during the manufacturing process, but also during any soldering process. As an MLCC cools down below the Curie point, there's an immediate increase in the dielectric constant, followed by a steady drop over time. Now, since capacitance is directly proportional to the dielectric constant, the capacitance will also decrease over time. This is called aging, and it's usually in the range of 1 to 5% per decade hour after the last heat above the Curie point, and this is indefinite. Now, the aging effect can be reversed by exposing the capacitor above the Curie point, and that's called de-aging. No matter where you are in the time curve, aging can always be reset back to its original starting time. So you have to ask yourself, when do we measure the capacitance? Since it's kind of a moving target. Now, manufacturers publish a referee time or reference time on our data sheets. Referee times are the number of hours after the last heat when a capacitor is measured against the specification. For most X7Rs, the referee time is 1,000 hours. For some higher capacitance X7Rs, the referee time can be 48 hours. So this means that after your last heat, after 48 hours or 1,000 hours, depending on the spec, that's when the capacitor is going to be plus or minus 10%. And we see this where people solder the MLCC to the circuit board, and then they immediately measure the cap, and then it's out of spec. You actually have to wait until 1,000 hours, or you can use our aging rate calculator on KEMET.com that can predict when that will happen. So you don't actually have to wait 1,000 hours. You can predict what the cap's going to be 10 hours after the last heat based on what it should be at 1,000 hours. It's important to note that class 1 MLCCs, again, are ultra stable, right? So this has no effect of de-aging for class 1 MLCCs. Another factor to consider is the equivalent series resistance, or ESR, and that represents the total ohmic losses in any capacitor. At lower frequencies for MLCCs, the ESR is dominated by the dielectric thickness. by the dielectric losses, while higher frequencies, the ESR is dominated by metal losses in the electrodes. This plot shows a class 2 X7R versus class 1 C0G from 100 hertz to 100 megahertz. Now, since class 2 MLC or X7R MLCCs are made from a barium titanate dielectric, under AC excitation, they have domain wall heating, which causes higher losses as compared to a class 1 C0G. Since class 1 MLCCs don't have that domain wall heating, their ESR losses are much, much lower. In fact, class 1 dielectric losses are usually so low, they're considerably harder to measure. This is why ESR measurements for C0G capacitors are very noisy in the low frequency region. And some suppliers, and for some of our part types, we can't even measure in those very low frequency regions because the dissipation factor is very, very low, which means the Q is very high for the capacitor. And sometimes you have to be very, very careful with the compensation and calibration of your meter because the fixture losses can directly affect your measurement. Not so much with class 2s, you get away with a little bit of fixture losses, especially in this lower frequency region. So one of the key factors that's influenced by ESR is the ripple current. Now, as current increases, I2R losses cause heating in MLCCs, and high enough currents will cause thermal runaway and eventual failure of the MLCC. Now, power is dissipated in the MLCC based off the I2R losses, and you can calculate based on the ESR and current and the thermal resistance of the MLCC what the expected temperature rise is based on your conditions. So for example, if you have a capacitor with an ESR of 40 milliohms at 5 amps RMS and an R theta of 32 degrees C per watt, you can calculate the dissipated power in the MLCC and the expected temperature rise. And the goal is to make sure that you're in these safe zones, right? This lower risk region is where you really want to be, less than 25 C temperature rise. You can get into this medium risk depending on your application, but you definitely want to stay out of this high risk red zone. And you can see based on the low ESR of class 1s, you get much higher ripple handling capability as compared to an X7R. Again, class 1s, that's why we see them in resonant converter applications, wireless power transfer, because you're going to have less I2R losses. So to summarize the differences between these dielectrics, right, class 1 versus 2 and 3, class 1's timing, tuning, pulse applications, applications with high current, resonant, class 2 really for decoupling, or 2 and 3, right, decoupling, bypass, filtering. You'll see transient voltage suppression also for those dielectrics. So depending on your application and your needs there, it's really going to choose where you're going to be from, which class you're going to go after. For volumetric efficiency, really you're going to see that class 2 or 3. If you need the stability plus high capacitance in the class 1, you're going to have to use a lot of them as compared to class 2 and 3. Class 1s have much more temperature and voltage stability as compared to 2 and 3, but you are going to have much lower ESR again in class 1 with higher ripple current handling capability in class 1. So you kind of use this table to help guide you with your application on which class you want to go to. When you get to the subclasses, X7R, X5R, C0G, you can get a little bit more specific as to which dielectric you're going to need based again on your application conditions. All right, some of the key takeaways: ceramic capacitors again come in many different sizes and many form factors. You really have to look at your application conditions. It's going to help you drive you to what form factor that you're going to decide to go after. Again, MLCCs are constructed using alternating layers of ceramic dielectric and metal electrodes. Many different dielectrics can be used to make MLCCs, so depending again on your application, which dielectric you're going to choose. And again, choice of class, I should have just repeated that. Choice of class and dielectric is determined again by your application requirements. So, again, when you approach what capacitor to select, it's good to really have all your application considerations, vibration, temperature cycling, maximum, minimum operating temperature, your mission profile. And that's really going to guide you to the best selection of the type of ceramic capacitor that you're going to use in your application. So thank you, and we'll go and pass this off to Daniele. Let me stop sharing my screen. Stop sharing. There we go.
Okay, Daniele, you're up.
Yes, 1 second. Can you see the screen?
Not yet.
Oops.
It's
now?
coming, Daniele.
Okay, thank you very much for the introduction. 1 second, that is working. Okay, my name is Daniele Zanarini. I'm product manager for Film Capacitor. I am an electrical engineer. I took my degree in the University of Bologna, and I am employed in KEMET since 2007. Before I was an R&D engineer, and then I moved to product management since 2013. Today, we're gonna have a look into the basic schematic of construction of a film capacitor, the flow chart for the production to understand the basic steps and the different technologies. Also, an overview of the main dielectric that can be used for the film capacitor. And we will have a talk also on the self-healing property, which is one of the most important property of the film capacitor. Also, an overview of the different type of metallization that we can have on this technology. And finally, a very quick portfolio overview. So the most simple film capacitor technology is the so-called single metallized parallel construction. So basically it's characterized by the winding of two film metallized, one upon the other. As you can see, we can have this wound shape. Basically, the construction, let me, okay, here. Basically, the construction is characterized by overlapping two film that you can see in the picture. One is this one, and the other one is that one. And as you can see from the picture, the metallization is in the orange, orange color, and the dielectric is the blue color. Some characteristic of this is that not all the film is completely metallized. As you can see here, there are some parts that of the film that are not covered by metallization. This is called offset, and this is used to avoid short circuit between the one of the polarity versus the other. When the capacitor is charged with the voltage, we have here the creation of the electric field. The basic, let's say, equation of the capacitance is given by the relative permittivity of the dielectric multiplied by the absolute vacuum permittivity multiplied by the area, which is the total area of the overlap between the two films, and the dielectric thickness, which is actually the thickness of the dielectric that we are going to use to build the capacitor. As you can see from the picture, in the reality, the thickness of the metallization and the thickness of the dielectric, even if in the picture looks very similar, are completely different in terms of magnitude. In fact, the metallization is in the range of 10 to 20 nanometer, while the thickness of the dielectrically typical is in the range of 1 micron up to 12 micron. When we apply voltage, as we said, we create an electric field between these two layers of film, which is calculated dividing the voltage applied by the thickness of the dielectric. If we consider the energy density, so the energy divided by the volume, we can see that we have this kind of relationship. So the highest electric field we can create, the highest energy we can trap inside the capacitor. Of course, there are some limitations because it's not possible to ultimately increase the voltage applied to the dielectric. So always is a matter of compromising, considering, let's say, the maximum energy that we can store, the maximum electric field that we can apply without damaging the capacitor. So having an overlook to the wall construction, we can see that more than the wound element, we also have some spray material that is applied on the wound element. And then we have also some wires. The end and the spray termination and the wires are used to make possible connection of the capacitor with the outside circuitry. Of course, this is just an example because we could have a different termination So not just wires, but male or female terminals to have a direct mounting on the bus bar or others. Then the capacitor is typically allocated inside the plastic box and covered with resin. So we said that the main and the most simple schematic is the parallel construction, in which we have all the voltage that is applied to the single layer of the dielectric. But we can have more complex construction where we play a little bit with the metallization in order to create internal different section in order to split the voltage across these different sections. So in this case, this is the typical schematic of a two series construction, when we can see that the first film is connected to one polarity and the other polarity with a bridge inside without metallization, and the other film is basically completely metallized in the middle with two offset of not metallized part here and here. So inside basically create a two series construction. Of course, we can iterate this construction with the 3 series or 4 series, and in this case, we're going to split the voltage into more and more series. So this can allow the capacitor to work with higher and higher voltages. If we have a look to the basic flow chart of the construction of the capacitor, we can see that everything starts from the plain film. This is basically our master reel, so the film is not metallized at the beginning. Consider that this master reel can be large from 600 to 900 millimeters. And the first step of the process is the metallization of the film. So basically the first step is applying metal over the film plane. Some of our other competitor does not have the possibility to metallize the film internally. We have this possibility. So for us, the process starts really here. And the apply of the metallization is made by a process of evaporization under vacuum. Once that the film is metallized, the big reel are cut into smaller reels that are used to start the winding process. And here we have the first big difference between the two most common technology for winding. One is the wound technology, which is, let's say, the most popular. And in this case, we are basically winding each element by itself around a round core. After the winding, we have the spray phase. So we apply additional conductive material on the termination of the element. Then we have some thermal treatment for the mechanical stabilization. And finally, the assembly, where we apply some wires or other type of connection. Finally, we have the electric testing before shipping the parts. So this is the results of the element inside the capacitor when we have the wound construction. The other possibility is to have the staked construction. So in this case, we are winding capacitor not each by each, not one by one, but around a flat core that we can put in after inside a big frame. After we have similar treatment than before, so we have the spray, we have the thermal treatment for stabilization, and after that the main difference is that here we take out these big bars and we cut into small elements. So here we obtain the final capacitor starting from big bars and then cutting into single elements. After that, we have similar steps than before. So we have the final assembly where we can put a lead frame or wires and then put inside a box with resin, or they could be also naked in case of SMD technology. And finally, we have the electric test. So you can see that basically the difference of the shape of the two technology. One is, I would say, a kind of a rectangular shape, while the other is oval shape. We said that the film capacitor are based, of course, into the film technology of different dielectric. So this is an overview of the main dielectric that are used to produce film capacitor. The most popular is the polypropylene. This is covering a big percentage of the application and is used only with capacitor through hole, so not for SMD. Also, we have additional 3 common dielectric that are PET, polyethylene terephthalate, PEN, polyethylene naphthalate, and PPS, which is polyphenyl sulfide. These are used for through-hole technology, but also for SMD technology. So let's have a look to see which are the main differences between these dielectrics. So we said polypropylene is very common. The constant dielectric of this material is 2.2. There is a wide range of thicknesses available. The thinner at the moment commercially is the 2.4 micrometer. The dissipation factor is very good. So it means that this dielectric can be used for application where there is a high ripple current because the ESR of the capacitor will be relatively small. Also, it has good property in terms of stability of the capacitance over temperature. The typical application, the typical temperature for working condition of the capacitor is in the range of 85 degrees with a maximum in the range of 105 or for very short time 125. It also has a good performance in terms of dielectric breakdown. So this means that I can use this capacitor in design where I want to apply a high electric field. So we remember from the previous formula that the electric field is given by the ratio between the voltage applied and the thickness of the dielectric. So it means that working at a very high condition of volt per micron, I can increase the energy density of the capacitor. And one of the other properties, good properties that is a typical characteristic of the polypropylene is the self-healing. So it is the property of the material to self-regenerate itself when a peak of voltage is reaching the capacitor, so that it can avoid the short circuit failure mode and failing in open mode with a relatively low loss of capacitance. The limitation of this material, the main limitation of this material is the temperature. So this dielectric cannot work at a very high temperature, so it has a relatively low melting point and is not suitable for SMD process because the temperature of the dielectric will not overcome the SMD reflow profile. The other dielectrics that can be used have different characteristics. So basically are more withstanding with a higher temperature. So they are the best characteristic of them. So they can be used for SMD mounting, for SMD reflow profile, but have, let's say, other lower characteristics. For instance, considering the self-healing, which in which the PET has, let's say, medium performances, but even lower compared to the polypropylene. The PEN medium low and the PPS low. In terms of let's say stability of the capacitance over temperature, the best solution is PPS. So these 3 dielectric are not, let's say, so popular, and they are used especially for SMD technology where the high temperature withstanding is necessary to overcome the reflow profile. But as I said, the polypropylene is, let's say, the most diffused dielectric used in film capacitor technology. Also considering the stability of the capacitance over frequency, or the tangent delta or dissipation factor over frequency, we can see that the best dielectric in this case are polypropylene and polyphenol sulfide. The other two dielectrics, so the polyester, have less stability in terms of capacitance over frequency, and also they have a higher dissipation factor over frequency. So it means that they cannot be used for application where a high ripple current is necessary. So to summarize, for the polypropylene, we can consider as a key advantage the possibility to handle high current, high voltage, and high frequency, but the key limitation is the temperature. So it cannot work at a very high temperature. The typical application are power capacitor, pulse, as I said, where the amount of current is very high, and also EMI filtering, where the self-healing properties is mandatory and very, very important for the application. Considering the PET, the key advantage is the high working temperature, because as we said, it can work at a higher temperature. It can handle medium power, and the main limitation are related to the high frequency, where the dissipation factor become quite high. So the current should be limited. Typically is used as a coupling or decoupling capacitor, and also DC filtering when the current requirements are not so high. Considering the PN, the main characteristic and advantage is the high working temperature. But as we said, and very similar to the PET, the limitation is given by the high frequency and the power that should be limited. Typical applications are coupling and decoupling. The PPS has a very high characteristic in terms of stability, but due to the low self-healing, we don't want to use this dielectric in high power application. So we should be careful using this dielectric in such application. Typical application is filtering, but with small power implied. We said that one of the most important characteristics of the film is the self-healing property. The self-healing property is the property that make the film capacitor able to fail into a open mode instead of having a short circuit. So let's see a little bit what happens. If I have inside the film a weak point, or I apply a peak of voltage that could happen inside the application, I can have a flow of current from one polarity to the other polarity of the capacitor. This current flowing in this direction can generate high power, and this high power leads to an increase of temperature that will lead finally to the vaporization of the metallization in that area. So as you can see from the picture, this is a picture of the self-healing. You can see that the black area is the one metallized, while the other area is the one that the self-healing occurred. So in this case, we have the vaporization of the metal in that area of the breakdown channel, and we have the insulation of this part. So the capacitor has lost a little bit of capacitance, but has avoided to have a short circuit. Of course, the characteristics of the self-healing are given by many factors. One of the factors, of course, is the dielectric itself. So we have, as we said, for instance, for the polypropylene, we have some dielectric that, due to their chemical composition, have a better property themselves. to have a good self-healing. But this is not only the one characteristic that is determining the good self-healing or a bad self-healing. As we said, during this process, we have the vaporization of the metallization. So you can understand that the thicker the metallization is, the most difficult is to have this vaporization and to have a good self-healing. So, of course, also the metallization design, the quantity of the metal that is applied on the dielectric makes some difference in the way of the capacitor can self-heal. So the thinner the metallization is, the better the self-healing is. Of course, the metallization is always a compromise. So at this point, we could say, okay, so we keep the metallization very thin so that we can improve the self-healing capability. But of course, the metallization has an impact on the current capability. So the metallization is part of the electrode of the capacitor. And so you can imagine that the thicker the metal is, the lower the ESR will be. So basically, we always have to consider a compromise. In case of thin metallization or single side, like we said until now, we can have quite high energy density, but we have to compromise a little bit in terms of current capability. By the way, up to now I've discussed only the simple metallization, the flat metallization, where the thickness of the metal is constant all over the film. In reality, we have also other technique that can increase the quantity of the metal into the contact area, so where the current is higher, and decreasing the thickness of the metal where the current is decreasing. So this is a compromise, let's say, between having a high current capability and good self-healing. Of course, we can have also other design where we can increase the capability of the current. So for instance, we have some series where the dielectric is not metallized, but actually there is another layer of film which is double metallized. So in this case, with this construction, we can really improve the characteristic of the capacitor in terms of DVDT, peak of current, and also current RMS in the application. Of course, in this case, how we'll have to manage carefully the self-healing. So how we'll have to reduce the volt per micron applied to the series. Going again to the left, we have the situation with some series where the metallization is not applied on the dielectric, is not a double metallized, but is a real film foil of aluminum. In this case, we can reach the best performances in terms of current capability, but of course, we will have to compromise in terms of volt per micron and so in terms of energy density. Just a quick overview. As you may know, the film capacitor can have really different shape, different dimension. We go from capacitor that are actually weighing some grams up to big capacitor like the brick type that can weigh up to 40 or 60 kilograms. Normally, we divide the portfolio into two parts, the so-called DC film that are characterized by low power. In this big family, we find, for example, the SMD capacitor or other special component that can be used, for example, into DC application for automotive, for suppressing noise into the DC motor. We have the general purpose. We have the EMI, which is a big family that includes the X and Y certified capacitor using for the suppression of the electromagnetic disturbs. And also we have pulse capacitor that are typically used for resonant converter or snubber. And then we have the family of the AC, where we consider capacitor for high power. Here we have different but typical application are, for example, the DC link, and we can find solution in box or metal or plastic can, or even a square shape like the big brick. Other typical application are AC filter. So for instance, used in solar or wind inverters. And this can be of different shape in box or aluminum cans. And also we have the pulse and the snubber that can be also used in solar and wheel application. And as you can see, we have special lugs that can make this capacitor mounted directly on the power module. So some takeaway from this discussion. We have the basic construction of the film capacitor is the so-called parallel construction, but we can have also multi-section or series construction in order to increase the possibility of the capacitor to work at a higher voltage, dividing the voltage into different sections. The main technology is the wound capacitor and the stacked capacitor. We have seen an overview of the different dielectric. Each one has different characteristics in terms of temperature, in terms of self-healing. And so we should really check carefully the selection of the proper dielectric according to the type of application that I need. We also had an overview of the most important, I would say, characteristic of the film capacitor, which is the self-healing. So we said that the self-healing is not only driven by the chemical characteristic of the dielectric, but also the metallization. And the metallization is always compromised between the possibility of carrying high current and the good self-healing. So really, depending on the characteristic of the application, we can play with some variables in order to increase the energy density of the capacitor, so the allowed electric field, or we can increase the current capability, but we have to compromise on the electric field applied to the capacitor. I think this is the last.
Okay, thank you, Daniele. Let me share my screen here and we'll get to our Q&A portion. So thank you, Daniele. And we'll now open it up for questions in the last 7 minutes that we have here. Obviously, as I mentioned earlier, please submit any questions that you might have through the Q&A window of the Zoom meeting. And if you have some questions that come to you maybe a little bit later after we're done, you can submit them through the link there on the screen. And Daniele, since you just went, we had a question for you. There was this one particular person had a question about wanting some clarification as to what is the purpose of the spraying, that spraying that you mentioned. They asked, well, is that some type of dielectric? What is the spray that you mentioned?
Yes, so when you wind the capacitor, basically you have already the capacitance. The capacitance is there. But the problem is you have to connect the capacitance outside to the rest of the world to make it usable, right? So we are going to apply this spray material, which is a conductive material, in order to create, let's say, determination. After that, we can finish the capacitor applying additional wires or other lugs. For instance, if we are thinking about this kind of snubber capacitor, for example, to be mounted on a power, on the IGBT, for example, on a power module. So actually the spray is conductive, of course, and is a way to connect the capacitance that is inside the winding to the outside world, I would say.
Okay. And I have one more for you, Daniele, then we'll move on to Mark and the remaining minutes for MLCCs and ceramics. So Daniele, when you mentioned short time, as far as temperature exposure for polypropylene at 125, what do you mean by like short time?
Consider that the typical lifetime of this capacitor, it's in the range of 100,000 hours. When we work with polypropylene at 125, at the moment we have to limit the time, and the time right now is in the range of some thousand hours. We are going to release a new series in this link type, where we will increase this capability. So basically we will be able to work into this condition for 4,000 hours, which is much better, and it's a typical range of timing for automotive application.
Okay. And grazie, Daniele. We'll move on to Mark and MLCC. Mark, is there a rule of thumb for choosing a decoupling capacitor with respect to its voltage rating, considering its DC bias specification?
There's not really a general rule of thumb, but that's one of the benefits of KSIM. You need to know for your application what the minimum capacitance requirement is for the application, and then you can look into KSIM at the temperature and voltage of the application and look at the capacitance that you're actually going to get from the part type. So as you go smaller in K size, the effect may be greater in terms of cap loss. So you have to consider that. Choosing a higher capacitance, a higher voltage, maybe 2 times what you're using in your application, will have less of effect, of course, because you're applying less voltage across the MLCC, so you're going to get less capacitance drop. So definitely a good idea to go into KSIM. Just watch KSIM 3.0. You can look at the VCC effects with voltage and see if that's going to meet your application requirements.
Okay. And there was a bit of a clarification here as far as the temperature range of X7R. At one point you say minus 55 to 175, but then you have another slide that says minus 55 to 125. So why the difference?
Oh, so that's a really good question. So per the EIA 198 spec, X7R has an operating temperature of minus 55 to 125 with a capacitance shift of plus or minus 15%. That's the spec, that's the standard. You can use an X7R beyond that, again, if it's qualified, and we have an X7R series that we've extended the operating temperature out to 175C, but past the 125C range, so in between 125 and 175, it's no longer, I guess you would say, considered those X7R per EIA 198. So in the operating temperature range up to 125, you're going to be plus or minus 15%, but as you go above that, you could see capacitance loss. I was just looking at the data sheet, of minus 50% at 175. So it's the EIA that defines the operating temperature, but suppliers can extend that operating temperature if it's qualified to go beyond that.
Okay. And then another one here, what is the normal temperature rise for X7R and X5R? I know, Mark, that there's application considerations there, but maybe you could do it in a relative term.
Yeah, well, there's not a normal temperature rise for any MLCC. I mean, the temperature rise is a direct calculation of the power dissipated and or power dissipated due to I²R losses and the thermal resistance of the MLCC. To operate it safely, you want to stay below 20 to 25 C. So really considering what your ripple current is going to be through the MLCC. But MLCCs may not have any temperature rise because you're not putting any current through them, and it just may be the ambient temperature of the application.
Just thinking though in relative terms, right? Under equivalent conditions, which one would rise in temp more, X7R or X5R?
Oh, you mean X7R versus X5R?
Yeah, I mean, the question wasn't particularly clear, but I think that's a better way to think about it is, which one would heat up more, so to speak.
It all depends on the ESR, the part type, and the R theta, so the design of the part type. So, you know, if you have a standard X7R, same cap voltage versus an X5R, you might see similar temperature rise, but that's really going to be looking again at KSIM and being really part number specific at that point.
Okay.
But I would say similar.
Okay. And well, okay, that brings us to the end of the presentation. Thank you, Mark. Thank you, Daniele, and thank you everybody for joining. You will be receiving, if you have registered for this webinar, you will be receiving an email that has a link to the recording of the webinar, as well as a place to go download these materials. So look for that sometime tomorrow as in your inbox. And before we finish off, really quickly, please be sure to join us for next week's webinars, where on Monday we'll be covering a lot of the same topics on tantalum and aluminum electrolytic, as well as on Wednesday, myself and a couple of our FAEs will be dispelling and discussing some of the top capacitor myths that we see out in the field. So that should be a fun one. So join us for that. And please register on ec.kemet.com. And with that, we'll close it out and we'll see you at our next one in our global webinar series. Thank you very much. Goodbye.